Okay, so what we're gonna discuss today and maybe tomorrow, not tomorrow, the next two lectures are going to be about this PAC learning framework. Okay, and then so let me start with an overview about this PAC learning framework. Okay. So, overview. So we said the machine learning algorithms. I mean, it's even not so obvious to say when machine learning algorithm is correct. It's not even obvious to say when machine learning algorithm is correct because these algorithms depend on examples which are taken from some distribution. But what we want to really talk about is the property of the algorithm with respect to this unknown distribution. So that's what we want to say. Okay. So this PAC learning framework is an example, or maybe one of the most well-known and one of the most basic setup that attempt to specify when certain machine learning problems can mean. We want to specify when specify the correctness of a machine learning algorithm for a certain context. And although it's very limited. So in some setting that the framework doesn't apply in the sense that it say, I mean, the problem that we want to tackle is not PAC learnable, but it forms a basis of what we're gonna talk about in the future. Okay. So what we will study is something called the PAC learnability. So this is a bit like the description of a problem, okay, description of a certain problem. And I don't know whether some of you encountered the characterization of problems in complexity theory or algorithm theory. In that setup, we say certain algorithmic problem is NP complete, or maybe P-space complete, and so on. And then this PAC learnability is also a specification about the problem itself, not about a solution. Okay, but what this tells us is that we say certain learning problem is PAC learnable intuitively. So this intuition. Certain learning problem is PAC learnable if there is an algorithm that can learn or they can find a good hypothesis. Hypothesis can be a function or some set and so on. You can find a good hypothesis with only polynomially many samples. So we will describe exactly what we mean by the good algorithm, good hypothesis, and so on. But intuition is, in order to get a reasonably good hypothesis, meaning doesn't really matter. We will pick a particular choice of notion of good, but at this stage, your kind of informal understanding about what good hypothesis means, that's good enough. And this definition say we can find a good hypothesis just using only polynomially many examples. Okay, so the most important bit here is this part. So green, blue. This polynomially many is the most important part. Okay. So this algorithm is sometimes called something. So this polynomially many, not use samples, but for examples. But if you are familiar with computer science, this is a bit unusual because when we talk about characterized problems in computer science, we often characterize problem in terms of the existence of an algorithm of time or space complexity. Are there going to be a good algorithmic solution that only require polynomial time and so on? So in the context of learning, things are a bit different because we focus more on the so-called sample complexity, how many examples that we need to get a good hypothesis. And then later, we will refine, after introducing this pack learnability, we will refine this concept by efficiently pack learnable. And in this case, we say to learn a good hypothesis, the algorithm requires polynomially many examples, and also it runs in polynomial time. So there are problems that we will look at where the problem itself is pack learnable, so that just polynomially many examples is good enough to find a reasonable hypothesis, but it's not efficiently pack learnable. Okay, so there are examples like this. But then we will soon learn that this pack learnability, after discussing about pack learnability, we will learn an example of a so-called generalization bound. So one example of uniform generalization bound for a certain case, which is called a consistent finite set of hypotheses. And then this uniform generalization bound is going to be a very good tool that we can use to show certain problem is pack learnable. Okay, so let's give us a proof technique. For showing pack learnability. But this uniform generalization bound is only for a specific case. And as I mentioned before, pack learnability is very limited. In a more general setup, pack learnability doesn't really apply. So in that context, we will learn about so this is for a simple version. And we will also learn different uniform generalization bound for a complex version. And then this complex version, the shape of this complex version is the one that will appear repeatedly throughout the course. Okay. Then we will discuss a little bit about, so this is the setting where this pack learning say it's not pack learnable, but still, these are the kind of examples that we want to tackle in the context of in learning. And then this complex generalization bound will apply there. And also we'll discuss a little bit about how we should modify pack learnability and what kind of extra things we can say about this complex setup. Okay, so that's the big picture about the overview of the chapter 2, and that's what we're going to talk about. So let me start with the setup. So the setting that we're going to use in this lecture and also perhaps the first half of the course is a classification problem. So especially in this chapter, we're going to look at binary classification problem. What is binary classification problem? And then the problem is quite simple. We say that we have some input space. Typically, this input space is r to the n or r to the I, so it's a Euclidean space. And then we also have an output space y. But in the context of classification problem, output space is really simple. It's just binary classification case is 0 and 1. I mean, it can be -1 and 1, doesn't really matter. The output space only have a 2 element. And in our case, it's convenient to say the outputs are just 0 and 1. Okay. And then the goal of this problem, the goal of an algorithm that solves this classification problem is to find a function that goes from this input to the output. Okay. But if we are not given anything, we cannot find any kind of reasonable functions. So we are given a sample. So, and the output for the sample. Sample is a sequence of inputs, x1, x2, x1, and xn. So there are sequence of input together with output, y1, y2, and so on, yn. Then we want to find some function f that, in a sense, describe or it can be a good predictor that maps each of these xi to yi. So roughly speaking, this fxi should map to yi reasonably well. Okay. But the real context, so that's how the algorithm behaves. But the real context is we are assuming there is a hidden function C, which is called concept in the textbook, and then hidden function is map from x to y, and then each of these yi is obtained by applying this hidden function called concept. Then our goal is to find h, which is a map from x to y. Let's use h instead of f. That is closed, and that is very similar to C. So that's what we want to do here. Okay. And because the output is just 0 and 1, I mean, each of these function h can be also understood as a subset. If you take an inverse image of 1 that defines a subset, so the binary classification can also be understood as a finding an appropriate. So also the C can be viewed as a subset. So the binary classification can also be understood as a problem of finding an appropriate subset of X. Equivalently, this we want to find a good subset X is 0 of X. Okay, and then this X0 is obtained by taking inverse image of 1. So let me give you 2 examples about this type of problem. The first example is in the textbook. It's called axis aligned rectangle. So it's a problem of learning on axis aligned rectangle. Okay, so that's this problem. And how this problem works, in this case, the input space is just R square. And then the hidden concept, so which we want to find out from example, is just some rectangle. So I said this hidden concept, because it's a function to 0 and 1, can also be understood as a subset of the input space. So this hidden concept is some subset of the input space, which is a rectangle, okay. Bottom to top. So in the picture, we have a two-dimensional space, and then the concept is where we have a left and right and bottom and top. So, and it's a closed rectangle like here. Well, the goal is to find something that is close to this rectangle from examples. The examples are the examples we're gonna get are the pair of the input together with the corresponding output. So examples we will get, say, examples like this, and that will be marked to 0. If you get different examples that was here, it will be marked to 1. And another example here, it will be marked to 1 because it's inside the rectangle. And then other examples here, so on. They will go all going to be marked to 0. And another question is, given these set of examples, which I wrote as a bunch of axes in the two-dimensional space, I mean, how should we come up with some rectangle that is as close to C as possible? Okay. And so that's the first problem. So in this case, the concept is this rectangle, and then we're going to use this letter, this is curly C, which describe all the concepts. Our hypothesis H, which is also a function, that's also going to be a rectangle, different rectangle, L prime, R prime, B prime, T prime. And we're going to use H to denote this set of hypotheses. So in this case, they are the same thing. And from these examples, our problem is to find appropriate H. So what should we do about this? So that's the one example of classification problem. And then the other example of classification problem is the problem of learning. A conjunction of literals. Yeah. So in this case, we assume there are variables, binary variables, Boolean variable v1 up to vn. So v1 can have a value 0, and then v2 maybe have a value 1, and so on. And we have a value 0. And our input space X is going to be a configuration of these binary variables, or you can think of it as an assignment to these binary Boolean variables. Because each of these vi have a value 0 and 1, this X will have a space 0, 1 to the end. So each element of X specify the values of these binary variables. And Y is as before, it's just 0 and 1. And then the concept that we want to learn, so this set of concept, is going to be, if we express this as a logical or Boolean logical formula, it's going to be a conjunction of so-called literals. Literals are variables or its negation. So for instance, one example concept may be v1 and negation of v2 and maybe v4. And another example may be v1 and v4. Yet another example is v1 and v3 and negation of vn. So So non-example is something like V1 or V2. This is not an example. That's not a concept that we're going to consider. Okay, we are only thinking about conjunction of Boolean variable or its negation. Literals means Boolean variables and their negations. Okay. So the question is, given, so we are given, so there is some hidden concept C, which is, let's say the hidden concept is this V1 and V2 negation and V4. And let's say the n is equal to 4. So let's make it a bit simple. Four. And 4. Then we are given a bunch of examples. So the example is, say, if V1 is 0, 1, and V2 is 0, V3 is 0, V4 is 1. Then, so this is example 1. Then say the value of y has to be equal to 1. And then the second example may be V1 is 0, V2 is 0, V3 is 1, V4 is 1. Then we say this y2 has to be 0 because this 0, 0, 1, 1 doesn't satisfy the concept and so on. So we are given these examples. So and then from the question is, from these examples, find a conjunction of literals that is close to C. So this is the second learning problem. So, I mean, maybe just to digest these problems, I will give you 2 minutes to think about what would be a solution. So suppose you don't know anything about, PEG learnability. I don't think you know anything about PEG learnability at this stage, but just, suppose that we are given these 2 problems. How are you going to go about it and just come up with some solution? Okay. So I will give you 2 minutes to think about it. Right. So I think the Inson gets some good idea. I mean, if you generalize your ideas, then you're gonna, you can come up with a learning algorithm that I'm gonna explain. Okay, let me tell you about one approach we will study and we will analyze. That approach is really simple. For the first problem, what we're gonna do is that we just look at the positive examples like this, the one that's marked with red, the number that were marked with 1 for the first case. Then try to draw a rectangle, which is a tightest. So we just draw a rectangle. So suppose there is one more here. So then we draw a rectangle. We draw a rectangle that is the tightest here. So like this. And maybe in the more general case, there may be more positive examples in the inside and so on. But then there is a gap. So this is what our algorithm will compute. And you can see that the computing this rectangle, so that's going to be what we will write as a H of S, so an output of an algorithm that we will study. We see that this algorithm is not perfect. I mean, there is an error. The regions that you see here, and this region that goes here and so on, something like this. And this region is the difference between HS and the concept C. And HS is always a subset of this C, the target concept that we are aiming at. But there will be some gap between them. And then what we're gonna analyze is that how bad is this gap? Okay, and then it turns out this gap is not very bad in the sense so that we can still, according to the definition of PEG learnability, this algorithm that I just gave you is a PEG learning algorithm. So that's one approach, and then we're gonna analyze this algorithm. The second approach is a bit, I think it's in line with what Insun has in mind. So the way the algorithm works is like this. It look at only positive examples like this one. And then from the positive, so initially the algorithm say every return is possible for the conjunction. So we consider V1, negation of V1, V2, negation of V2, V3, negation of V3, and V4, negation of V4. But then you look at positive examples one by one, and then so you look at example X1, and then if a literal doesn't appear in the positive example, we get rid of it. So for V1 case, we have a V1, but not negation of V1. So we get rid of this negation of V1. For V2, we have negation of V2, but not V1, and now not V2. So we just get rid of this. V3, we have a negation, so just get rid of this. V4, we have 1, so we get rid of negation. Now suppose the second examples are the, right. So and so on. So then in the next example, we do exactly the same thing for the remaining literals, and we continue to do so until we process all the examples. And then we will show that this algorithm is also has a very nice property. In other words, this algorithm is a PEG learning algorithm that I'm gonna explain to you next, okay? And by the way, the intuition behind these two algorithms are very, very similar. So the intuition behind the number 2 and intuition behind number 3 is that we only look at positive examples. And then based on the positive example, we try to come up with as tight hypothesis, but as strongest hypothesis as possible. So that's the intuition behind these two. And in this context, this intuition leads to good learning algorithms. Okay. Now, so then we move on to our next topic, which is how we can formally describe the correctness property of these algorithms. And the PEG learnability provides one answer about this. Then this definition, when you see it first, it may look intimidating, but as I said, in some sense, the definition is not so bad. Okay, but before talking about PEG learnability, we need to introduce a few concepts. So here's a reminder, we are thinking about the binary classification problem. So we have input space and output and set of concept, and then one concept that's C, and then we have a hypothesis set, and our goal is to find the hypothesis set. And also something that I didn't really talk about is that we are assuming there exists some distribution. Okay. We're gonna, the definition will quantify about the distribution, but there is some unknown distribution on X. And then for the binary classification problem, it's given the sample, which is a sequence of input together with corresponding output by 1 to 1, which is computed by using C. And something that's unknown in this case is this C. C is unknown, and the probability distribution is unknown. Okay, so in some sense, the goal of the learning algorithm is to find something that behave like C with respect to the inputs drawn from this unknown distribution. Now, what's the definition? And to talk about the definition, we have to introduce two concepts. One is called the risk or generalization error. And this is something that I explained to you in the first lecture, and then also it amounts to what learning algorithm really try to achieve, the ideal aim. It's not exactly ideal aim, but it's related to ideal aim of learning algorithm. And what is it? It's defined like this for risk over H. H is from our hypothesis. And then this definition assumes there exists the concept C and then distribution D on the input. So although I didn't write C and D, this definition of risk implicitly parameterized by concept and the distribution. And it's defined by the probability of an error of a hypothesis. So it's a probability of H of X is different from C of X. So this is an error of a hypothesis with respect to the concept when X is drawn from D. And then that is, you can also write it as an expectation of so-called indicator function. So this function returns 1 if the condition is true, otherwise return 0. So same as computing this expectation of this indicator function. So that's the risk or generalization error. And then, so, I mean, in later, we will use some different notion of risk, but in all cases, the idea of risk is exactly the same. It's try to capture what we really want to optimize if we know everything. Like if we are, I mean, we can manipulate mathematics essentially, then what are the quantity that we really want to optimize? We are very, very powerful, you know, everything, what are the quantity that we want to optimize? That's captured by risk. In the context of binary classification, the appropriate notion of risk is defined like this here. So now, as I mentioned before, this risk is not computable, so algorithm can't really work on risk directly. So it has to work on some proxy measure, and that's called empirical risk. Or sometimes called empirical error. And that is defined by this. It's parameterized by hypothesis and concept and distribution, but at the same time, it's also parameterized by a sample, okay, which is a sequence of events which are drawn from this distribution D independent. So this is written as our head of S. And that is defined by average errors with respect to this, this sample. Okay, so that's the average error. And then this average error can also be written as like this, x over. I mean, I want to use this notation because it will appear a lot. So x. So this d hat, so this d hat is means it's called empirical distribution. But it's a distribution, it's a uniform distribution over the x1 to xn, in over examples in the sample. So use a different color. The important bit here is this R of H and R head of H. Okay, so these are the key, very important concept, the risk and the empirical risk. And one kind of okay. So in the machine learning or statistics, if you see hats like the one you see here, and also hat that you see here, they indicates we compute some quantity based on sample. Okay. So in this case, this quantity R head of S is based on the sample S that we talk about. I mean, we use here, and also D head is also defined over the sample. So if you see some quantity head, that means it's a sample version of D. So it's the sample version of D. Okay. Now, one easy property we can show is I think the one node behave strange. The one easy property that we can show is that some simple lemma is this. I mean, this is how people say our head S, the empirical risk, is an unbiased estimator. Unbiased estimate of RFS. And what does that mean is if you take an expectation, the over S, sample from D of M, then compute R head of S, and that's going to be equal to R of S, R of H. Okay. So this means on average, our estimate, this is a random quantity because of S. This random quantity on average is correct. It is exactly the same as what we are aiming at. Okay. And the proof is really simple. If you just unpack the definition of R head of S, and then use a linearity property of expectation and do some calculation, then you can easily show this equality is true. So I'm not going to go through this. So now using this empirical risk and so on, we're gonna define the path vulnerability definition. Say that our concept class, I want to use color concept class C is heck runnable. if there exists an algorithm, okay, so this algorithm take sample together with corresponding y's and produce a hypothesis, and a polynomial. Polynomial with 3 parameters. The textbook is more general, but I'm gonna use some simpler version that I think something strange is happening. So there is a polynomial such that the for all concept C and in the concept class, and then for any distribution on the inputs, which means that in any learning scenario, and then about the next quantification is about how good solution we want. So for there's epsilon and there's a delta, and then there we also talk about the number of samples m. And you say if certain condition is true, so then just write, yeah, if some condition is true, so then you said the probability that the risk of delta. So what this conclusion, let's just first try to understand what this conclusion is telling us. The conclusion tells us is that given the m independent samples, so given m independent samples, so this h of s is the output of the algorithm of A with when it's given this S together with corresponding y1 up to ym. So this y1 up to ym, they are computed by applying C to x1 and so on. And because S is random, what this algorithm will return will be random. So this h of S is random output produced by an algorithm. The algorithm itself is not random, but because the sample is random, this R of h of S is random. And then this upper bound is saying the error, the generalization error, or risk of h of S, what's returned by the algorithm, is very, very small. So epsilon is a very small quantity. Okay. And then delta is usually also very small quantity. And then what you say is that the error is very small with very high probability. So error may sometimes be really big. Most of the times, the error computed by our algorithm will be very small. Okay. Now, the big part of this definition is boils down to this if part, and then now the if part to say this kind of thing happens when we have enough samples. Okay, if m is greater than the polynomial over 1 over epsilon and 1 over delta, and n, I'm going to explain what n is. N is This n is the size of input. So in the problems that we talked about before, for instance, these problems of learning conjunction of variables, then this size of the inputs correspond to the number of variables. So the specific example we talk about, the number was 4, so this n is equal to 4, but n can vary. If we have to think about more variables, then n can be larger. Okay. So, and then so this is the definition of PEG. No, so it's not about for all epsilon or there exists data. So that's typically what people do. And I mean, I think the Shinyoung may be kind of remembering what the typical definition of continuity. So in the context of continuity, you want to say, if you want to improve the precision of the output, I mean, there's a way to do it by constraining the input. So that's why epsilon and delta comes with 4 and exists. Here, the story is different. What we want is that we want to control the accuracy of the algorithm, which is given by epsilon, as well as the probability of having this good accuracy, delta, at the same time. Okay. See, we want to control both. We want to reduce the probability of having bad case by picking very small delta. And then also we want to make sure what algorithm returns is very good. So we want to have a small epsilon as well. So now we have to pay some price somewhere. I mean, we cannot really reduce epsilon and delta as small as possible without doing anything. And the price that we pay is to increase the number of samples. Okay. So if we have a very small epsilon and delta, then this polynomial will become very large because 1 over epsilon will become very large, 1 over delta will become very large. So this polynomial will become very large. So then we will need lots of examples for, to have this required accuracy and high probability at the same time. Yeah. Does that, I hope, answer Shinyoung's question, I guess. Okay. Okay, so this is the definition of PEG learnability. PEG learnability say it's about property about concept class, a property of a problem. And then it said that concept class is PEG learnable if there is an algorithm and then polynomial such that any learning scenario, which is for C and for D, if we have, and then for any required accuracy of the algorithm and the high probability of the algorithm, as long as we have polynomially many examples, then we can achieve it. So that's what this definition is telling us. And the words, this PEG is an acronym of probably approximately correct. And then this approximately part is coming from epsilon. So we are thinking of, instead of saying the risk is equal to 0, so we are really putting some bounds about this, giving some kind of rooms to play with. Probably correspond to delta. It means a small delta, approximately means a small epsilon. Okay. Then we say, and yeah, one important bit is that this is mostly about sample complexity. And it doesn't say about how much time the algorithm will take. Okay. So if we require the algorithm should take polynomial time, we say this is PEG learnable. So for if A takes a poly time, A with respect to 1 over epsilon, 1 over delta, and n, A in addition. So then we said the prob concept class C is efficient, effect, vulnerable. And this A is called a peg learning algorithm. Okay. So it's efficient, effect, vulnerable, and it's called peg learning. So now let's go back to the example that I told you. So, okay. So using this definition, which means that for any learning context to achieve very good upper bound and then with high probability, we only need polynomially many samples. So that's the definition of PEG. So let's try to show that this the one example that we talked about, which is axis-aligned rectangle problem, is actually PEG runnable. So here's the lemma or some statements, so that the axis-aligned rectangle, the problem of learning an axis-aligned rectangle is PEG runnable. So that's what we want to show. And then, so to see why that is the case. And then this PEG runnability say we have to come up with good algorithm. At the same time, we want to have a polynomial form. So what we have to do, we have to design an algorithm A, and also have to come up with a polynomial on 1 over epsilon, 1 over delta, and 1. In this case, n is always fixed to 2, so it doesn't really matter. So we have a 1 over epsilon and 1 over delta. So what's our A and the polynomial? Our A is the tightest, the algorithm that I explained to you before. So finding tightest rectangle containing positive examples. So this can be computed in linear time. So if you have a sequence of examples, you just go through it, pick the one which is marked with 1, and then find the tightest rectangle that includes all of them. Okay, so that's is A. Now for polynomials of 1 over epsilon and 1 over delta is going to be the following. So 4 over epsilon, so 4 over delta. Now, the typical proof about this PEG learnability or generalization bound uses so-called uniform bound, which means that, you essentially you estimate probability of disjunction, multiple cases, by the sum of individual probability. Okay, so that's sometimes called uniform bound, and union bound. So so this number 4 is actually coming from this union bound. So how to prove this? So proving this is not so hard. So suppose think about the learning context. So we have a concept C. So what we are doing, we are fixing some concept C. We are also fixing some distribution D on the input. Then we are assuming there is a sample that's coming from x1 to xn. Okay. And then m is greater than this polynomial. And we want to show the probability, and then we will return a small rectangle, probability of our rectangle returned by this algorithm. So let's write it as a HS. Probability of this guy is small, is going to be large, 1 over delta. And then this is equivalent, the probability of R of HS is larger than epsilon. to smaller than or equal to delta. So they are the equivalent statement. And this is what we're going to show. Okay. Now, how to do this? So then here's the idea. So we have examples, positive examples, and also we have negative examples outside. Then based on the positive examples, our algorithm returns a rectangle. Let's make it a bit larger by a positive example. Okay. And then now what's going to be this error? So in this case, this is our H of S, and this is C. And then these rectangles include the boundary, and the error R of HS is going to be the regions that is going to be this region. It includes the outer boundary, but not the inner boundary. Okay, so that's going to be the error. I mean the probability of this region. So write it as the probability of this region. So we're computing this region. Okay. Now the proof goes like this. So we split this outer rectangle into 4 regions. I mean, not split into 4 regions. We are thinking about some 4 different splits. The first split, this. The first split will be based on each of the split will be based on each axis. Each axis. So the first axis we will split something like this. Find some point here that's going to be S1. This is a left, right, bottom, up. So we'll find S1 such that the probability of this part, if we include the boundary that's going to be greater than or equal to epsilon over 4, if we exclude the boundary that's smaller than or equal to epsilon over 4. So here's what we're going to do. So define the probability of the L S1 times T that is greater than or equal to epsilon over 4. And the probability of excluding this is going to be smaller than or equal to epsilon over 4. And by using continuity of mean, so if this, I'm excluding some degenerate case, but excluding degenerate case, and then if you use a continuity of probability, you can always show that there always exists something like S1. And you can do the same thing for the other. So this is with respect to, the one side, which is close to the y-axis. Then you can do the same thing for the other 3 sides of the rectangle. So they will give us S2 and S3 and S4. Then we say that this closed rectangle, we call it R1. And then the rectangle that's defined by the S2 is going to be R2. This is R3 and R4. So what's going on? So we have one thing like the blue one that you see over there. And we also have some black one Then we see here. So this will become S2, and so on. So we have a four side. So now let's the probability. Okay, so the probability of these regions, each of these the cut out side like R1, R2. If we do not include a boundary, that's going to be smaller than equal to epsilon over 4. So what this means is, if we now take the probability of all of those, so this part, this part, that's going to be bounded by probability of each individual one. And because each of them is bound by the epsilon number 4, that's going to be bound by epsilon. Okay. So what can we reason from here? So one thing we can reason is now. So what we want to prove is this guy. One reason is that if R of HS, suppose the algorithm returns this something HS greater than epsilon, then it cannot be the case that this the rectangle defined by HS, we take a, if it's greater than epsilon, then if the intersection of the Ri is equal to empty set for some why that is the case. If this rectangle of H of S intersection with Ri, none of them is empty. That means we are in a situation where this C is here. And then this entire error region is covered by the union that's described here. So it's all covered by these regions that's described here. And then we said the probability of this blue region is going to be bounded by epsilon. So that's in contradiction with this, the error region is greater than epsilon. So at least one of them has to be equal to the empty. And then, so what this means is to compute the probability, so it's I mean, this probability is bounded by probability of I rectangle of HS intersection Ri. Now we use, so it's sufficient to bound the quantity on the right hand side, and then the right hand side can be bounded quite easily. So this is, I mean, because I can be, there are 4 possibilities. We just take a union bound, which means that the disjunction of 4 of these cases, and that small probability of that disjunction is smaller than the sum of probability of each individual case. So it's I is equal to 1 to 4, probability of rectangle H of S Ri is equal to empty. But okay, what we do know is that in our, so what we do know is if the rectangles contains all the positive examples, so what this is telling us, so this tells us for the case of Ri is equal to 1. This tells us that the R, let's draw a picture. So we have situations where R1, this region is R1. Then this rectangle that we covered here, so this is HS. So in order for this to happen with m examples, that means we shouldn't have any examples in this region. Because if we have any examples in this region, the rectangle that we computed will intrude this rectangle R1. Okay. So and then the probability of having some example in the region is R1, at least the epsilon. So when we try make generate m samples, if the probability that none of the samples fall into this region, which has at least epsilon over 4, probability is bounded by like this 4 1 over 4. So, okay. So that's the bound of this quantity. And because of m trier that we have with this m, because this probability of this region is at least epsilon over 4, I mean the probability that none of the sample fall into this region is upper bound by this quantity. And then we can use formula. So this comes because 1 minus x is bounded by epsilon minus x. So this is always true. So what I mean by this is that when you generate the samples, so I mean, I didn't quite explain, when you generate x, which is a point in this two-dimensional space, sample from distribution D, and the probability that x falls into this region, this box. So the same, when this probability is taken with respect to x, that's a sample from D. Okay. So then if you compute this is the same as 4 times minus 4 epsilon, because m is at least epsilon, because m is at least, yeah. So if you just plug in the number for m, that's going to be number 4 over delta, and that will give us, all things are canceling, that will give us a delta here. Okay. So that gives us the bound for this probability. Okay. So this shows this specific problem is peg-boundable. Although, I mean, the explanation that I gave you a bit complicated. It's actually quite simple. Just divide each side for 4 different parts, and then that will give us a bound in this. I mean, that will give us to show what's required in the definition of peg-boundability. Okay, so I think maybe it's good to stop here, and then next time we will talk about some specific tools for showing peg vulnerability, and then look at some more examples. Okay, so that's it for today, and so thank you very much.